Good morning everyone, I am Dr. Manivannan, Associate Professor, Department of Computer Science, PSNA College of Engineering and Technology. So all of you welcome for the session of floating point addition in computer architecture. Right. So today the session is going to be solve how to add two floating point numbers which is in a decimal. Right. So now we start. What is floating point? So floating point which has a number with a precision points. Right. The standard format of floating point we have on three components. The first one is a sign bit which has one bit of sign bit to represent the value, and then the exponent values. The exponent value we have to represent in floating point in 8-bit, and last one we may call it as fraction or significant or Mandisa. So which has of equally 23-bit of single word floating point number. So single word is 32-bit. So 1 bit for is always a sign. The sign bit which must be 0 for positive, 1 for negative. So 0 if it's mentioned the sign bit, the MSB is 0, then the floating point is a positive number. If it is 1, then there is a negative value. The negative number, that is a sign number, it's a negative number. So always you have to represent the exponent value for the single word that is a 32-bit, that is a 8-bit we have to represent the exponent, and the fraction part is a 23-bit. So how to represent this floating point? That is minus 1 power s, that is s stands for the sign bit, which is multiplied with the fraction, the actual fractional number, and it's multiplied with the exponent value. What is the exponent? So the s bit is handled for zeros or 1 is either positive or negative. Then the fraction value is a 23-bit we have to represent, and the exponent in 8-bit. So this is the value we have to represent always of a floating point number. So totally 32-bit single word, that is called single precision floating point number. So if you are write, for example, it's a 1.0 is a binary number into 2 power 2. So this is a fractional number. The sign bit is a 0, right? So it may be call it as a positive number. Then the exponent value is 2. So why we have to represent this in a standard format, that is sign bit, exponent and fraction? Always the IEEE is a standard format of floating point to represent any floating point number to be represented as a format which is given here. So here is a positive number 0, so we are representing 0 here, and the exponent value is 2, so we have to represent 8 bits. So 0 0 0 0, so 4 bits. So another 4 bits, that is 0 0 1 0. So this is for 2, right? So 2 power 0 1, 2 power 1 2. So 2 power 1 2, that is 2 value, is exponent is 2. So we are using single point, that is 1 is here. Then we are using some of the fractional value. So we are replacing the floating point number into the standard format. So 0 it's for positive number, so sign bit is 0, and the value of exponent is 2. So 8-bit we are representing, that is 1 is a place of 2 power 1 is a 2, and the fractional part is 0. So all 32 bits, 23-bit is equal to 0. So totally 32-bit. Now we are representing the 1.0 into 2 power 2 as a standard floating point number, right? So now this is a basic of representing the floating point number into the standard representation. Now we move on floating point addition. Floating point addition, how two numbers going to be added. So there is an algorithm in architecture to add two floating point number. There is an adder which may perform addition of two numbers either in a whole number or in a real numbers. So now we are going to be seeing the floating point addition. So what is floating point addition? The problem is given to that, it's 0.5 which is added to, it's a negative number of 4375. So now the problem is going to be add two floating point number, which is the first one is a 0.5 and which is the second one is a negative number, we have to add 0.4375. Right. So before moving to the addition, we must know the algorithm of floating point addition. So what are the steps to be followed to solve this floating point addition? That must we know before moving to this one. So what is the algorithm in the architecture of the floating point addition? The first we are starting with the algorithm. So what is algorithm? That is implies with the 4 prominent steps to solve the floating point addition. We start with, and we have to check with comparison of exponent. Comparison of exponent is the first step we must follow doing our floating point addition. So what is comparison of the exponent? If two exponents are different, we cannot do any addition. So when the floating point to be added, all the exponents, that is two numbers, two operands exponent must be the same, right? So we must compare the exponent and equalize the exponent value based on the value. So how to equalize the exponent value? So which is the smaller one? The smaller exponent, the smaller value of exponent which equals to larger exponent. So that is the first step we have to do, the comparing the exponent, and we must equalize the exponent while comparing the smaller to larger. So what is smaller? If you have taken one operand value having the exponent of -1, the another value of -2, the -2 is a smaller. In terms of the negative number which is go larger negative number, that is a negative part, right? So -2 is a smaller than -1, right? If you have taken a positive number 2 power 1, 2 power 2, the 1 is smaller than 2. So positive number, that is a larger value, and the negative number which is a smaller value, right? So now that is the thing, when two values are given, we have to equalize the value. That is the first step. Either you do the shift right operation of the smaller number to equalize the larger value, right? So now the second step, we have to do the or the significance. So what do you mean by significance here? The significance value we are representing in the representation, that is 32-bit single word representation, fraction, mantissa or significant, which means the real part of your number, that is a floating point numbers, we have to add only the significance of the two numbers, right? We are not doing all the addition of the whole number, we are doing only the significance value. That is a second step of the algorithm. Second steps of the algorithm is add significant, right? Then we have to normalize. So what is the normalization? Normalize the sum. So when after you are adding the significance, we have to normalize. What do you mean by normalization? That is a normalizing of the sum, which means no leading zero in the floating point number. So we must normalize the number, then only it will be the number to be added for the floating point addition. So that is the third one, we have to normalize the sum. So how to normalize the sum? Either you are incrementing or decrementing, you are doing shift right or shift left to equalize the normalize the value of sum, right? So now we have to check the fourth step. So we continue here. The fourth step, we have to check overflow or underflow. So what do you mean by overflow? What do you mean by underflow? We have the representation of single word representation, we have the exponent value of 8-bit, right? The value of the exponent should be allowed within the 8-bit you have to represent. If it is exceeds 8-bit, we cannot represent any exponent in the single word, single precision floating point. If it is a double precision, it may be 11-bit. So either in 8-bit or 11-bit, you have to represent the exponent value, right? If it is exceeds, that is any one of the case of overflow and underflow. For example, the value should be on -26 to +127. So this is the value you have to use in the exponent value. If the exponent value it's implies within the lies between this -126 to 127, then there is no overflow or underflow. If the values, the exponent values -127, for example, that is called underflow. When there is a smaller negative number, we cannot represent in either 8-bit of single precision or 11-bit of double precision. We cannot represent. So -127, what may happen? This is an exception. If you take any compiler, either C or Java, whatever the compiler, if the value of very less of the negative number we cannot represent, we cannot do any kind of addition. So this is called underflow. When the smaller negative number is there, which goes on underflow. If the value of exponent is going to be exceed of 127, that is a overflow. The positive number of 128 we cannot represent in the 8-bit value in single precision or 11-bit value of double precision, which goes on overflow. So overflow or underflow is happened, any compiler will give you the exception. We cannot perform anything. So we have to check the fourth step. Either the value is in the exponent value is comes under overflow or underflow. If it is overflow or underflow, it goes exception. It goes on exception. If it is your value of -127 or +128, which means the value it's exceeding 8-bit or 11-bit, the overflow or underflow will cause you and which may go to the exception, So if it is happened, yes, that is exception. We cannot add two numbers. If there is no overflow, underflow, again we have to do the normalization. The final normalization. What is normalization? Normalize the value, no leading 0 in the whole pot, right? So we have to make it as 1 in a binary pot. That must be some value. If it is a decimal, there is a value on the whole pot. If it is a binary, we should use the 1 as a whole pot. No leading 0 for the floating point number. We are talking about floating point, so no leading 0 in the whole pot, right? Then check, still normalize. So still normalized. So if it is normalized, then we can done, right? So this is a fourth step, right? So if it is no, which goes to the normalization of the previous step, This is the algorithm. So very simple. The 4 steps we must follow of doing floating point addition. The first one, we have to compare the exponent and we must equalize the exponent. The smaller exponent should be equalized to the larger exponent. So once you are doing the normal equalization, then we have to add the significance, that is a fractional part of your floating point. Then third one is a normalizing the value, no leading 0 of the floating point number. Then we have to check the overflow or underflow. When there is a value sliced between minus 126 to positive 127, there is no overflow and underflow. If it is exits this value, there is an exception, maybe happen, we cannot do the addition. So after checking the overflow underflow, again we have to check the value of normalization. Still normalized, we can done with the value. If it is not, we have to again go to the normalization. After the adding the significant, we have to do the normalization. Let me try to explain the example of floating point addition based on this algorithm. The students must remember this algorithm before doing the addition, right? So this is the algorithm is followed in a computer architecture. The adder circuit will carry out this kind of addition, right? So now we move on to the example. So what is the example value? As I said earlier, the example is between 0.5 and which to be added to the negative number 4375. That is a negative number of 0.4375. So the value is given which is in a decimal, right? So all the computer must do the operations with the binary number. No decimal number will be processed at any cost. So we have to convert this value. The first step before moving to the algorithm, we must convert this value into binary. That is a mandatory part we have to do. So 0.5 plus it's a negative value of minus 0.4375 must convert into the binary value. So how to convert the binary conversion? So binary conversion of the first value of 0.5. So how to do? The whole part is divided by 2, as well as the floating point real part, that is a Mandisa part, is to be multiplied by 2 to convert into binary. So what is 0.5? We have to take only the fractional part. If there is any value in the whole part, we must neglect that and we should take the value of only the fractional part. So 0.5 is multiplied with 2, that is 1.0. Then again you have to take this fractional part, again you have to multiply with 2. But what is the value here? That is 0. If it is 0, it's multiplied with 2, always we are getting the 0 value. So we are skipping here. So now that is a value of 1. The 1 is for 0.5. So what we called, that is 0.1 into 2 power 0. So this is the actual binary conversion. So 0.5 multiplied with 2, we are getting 1.0. That 1 should be replaced in the fractional part, not in the whole part, because we are taking only the fractional part. If you are using the value of 1 in the whole part, the entire value is changed. It is not a true value. So 1 we are getting a binary bit, the whole part, that is replaced in the fractional part. So that is 0.1 into 2 power 0. The value is 0.1. There is a leading 0 in the whole part. We must normalize this one. No leading 0 in the part of any floating point number, right? If there is no 0, then only we can perform the addition. The adder circuit will work on, that is the value of 1. So we must normalize. So before going into the algorithm, we have to do these preliminary steps. Then only we must take the addition of two numbers. Now there is a normalize the value. So how to normalize? We have to either shift right of the value or shift left of the value to make a normalize. So point is here, we have to do the right side, right? Shift right of this precision point, because the 1 is here, no leading 0 will becomes once we have to move the shift right. So point is moved here, this value. So when you are doing shift right, that is a decrementing part of the value. So we have to 1 point we are moving here, that is 1.0, we are decrementing the value, that is -1. So 0 minus 1, that is 2 power minus 1. So this is the normalized value of 0.1 into 2 power 0. We are doing a shift right to make it as normalized. So that is a decrementing of value on the exponent, that is 2 power 0 minus 1, we are getting 2 power minus 1. So 1.0, 2 power minus 1 is the first value of 0.5. Similar, we have to take an off minus. So here you must very aware about that the given number is a negative value. So usually in a decimal floating point addition, binary addition, for the whole numbers we are taking 2's complement of the value, but in floating point addition we are not taking any 2's complement, only doing the addition we are taking a 2's complement, right? We are using this same negative number, the conversion also we are doing the same negative number. So what is the value? That is minus 0.4375. 4375. So this is to be converted into the binary value first. The binary conversion we have to do here. So how to use the binary conversion? Yes. So I already told you that is a conversion should be multiplied with 2, only taking off the fractional part of the number. So 0.4375 is multiplied with 2, right? Multiplied with 2, 0.4375. So what is the value? 0.8750. 0.8750. When that is 4375 is multiplied by 2, we are getting 0.8750. Now we are taking this fractional part, that is 0.8750, which is multiplied with 2, right? What we get usually, that is 1,750, that means 1.750. Again we are taken this fractional part, it's multiplied with 0 until we are getting the 0 as a multiplication value. So 1.5. So 750, it's multiplied with 2, it's 1.5. Now we are getting 0.5, it's multiplied with 2, we are getting 1.0. So when this fractional part 0, all the multiplication will give the zeros value. So this is the top to bottom value we have to replace in the fractional part in the place of 4375. So what is the value? Negative value, we are getting 0, 1, 1, 1, it's 2 power 0. So this is a binary conversion of that floating point number. You never skip this negative value, that is very important. When you are doing the significance value, we have to take a 2's complement. So 0.0111 into 2 power 0. Now again there is a normalization, there is a leading 0, we cannot do any operation. So we have to normalize this value. So how to normalize? We have to shift right, because 1 is here, the precision point is here, we have to make it as 1, right? So how many points we have to shift right? That is 1, 2. We have to do the 2 points of shift writing. So minus 1.11, it's a minus 2. So what is the value? Is minus 2. So minus 1.11 into 2 power minus 2. So first value after normalization we get 1.0 into 2 power minus 1. The second value is a minus of 1.11 into 2 power minus 2. So this is the actual value. Before we are going into the algorithm, we must do this kind of conversion, that is binary conversion. Let me normalize, and the binary conversion again we have to normalize the value. So two values we are getting, we can point it here, 1.0 into 2 power minus 1 and minus 1.11 into 2 power minus 2. So this is the value. Clear, students? So this is the value. The decimal number is given as a floating point. We have to do the preliminary steps of binary conversion and normalization, the second number binary conversion and normalization, right? So we have to do the normalization. That is a very important point, right? Now we move on to the algorithm, actual adder circuit, which involves the addition algorithm. We have to move into the addition algorithm. So what is the 2 value we are getting of 1.0 into 2 power minus 1, which is to be added minus 1.1 into 2 power minus 2. So we are going to be adding these 2 values, right? So what is the first step of algorithm? Equalize the exponent value. We have to compare the exponent which is smaller, that will be equal to the larger value. So equalize the exponent value. That is the first step of your algorithm, that is equalize the exponent. So which is the smaller exponent here? That is minus 2. Obviously that is minus 1 and minus 2. If it is a negative number goes larger, that is a smaller number. So minus 1 and minus 2, we are comparing minus 1 to minus 2, which is the smaller one. So what we do, we have to equalize the minus 2 into minus 1, taking the part of minus 1.11 into 2 power minus 2. You never to be neglect this negative, that is very important doing of the next step of adding the significance, right. So minus 2. Now we are going to be equalize this component. So how to equalize this component? Minus 2 should be a minus 1 value. So what should we do? We have to add 1, then we have to get the minus 1. So we have to incrementing the exponent. So when there is a incrementation, what we do, the precision point should shift left of the floating point number. Shift left will do the incrementing of your exponent. So what is the value? It's a minus, the point values here, we are shifting left of 1 point. So minus 0.111 into 2 power minus 1, right. We are incrementing. So we do the shift left, the precision point is here, the 1 point we should be shift left. So this point should be comes here and plus 1 is added, sorry, minus 1 we can get. So now both the values are equalized, the exponent values are equalized. 1.0 into 2 power minus 1 minus 0.111 into 2 power minus 1. So this is the value we are going to be do the addition. After the first step of algorithm, that is equalize the exponent, we are comparing the exponent value. The smaller exponent value should be equalized to the larger exponent value. Here minus 2 is a smaller, so we are doing adding incrementing by 1, the point should be shift left, the precision point doing the shift left for the incrementation, right. Clear, right. Now we are going to be do the second step. So what is the value here? 1.0 into 2 power minus 1 plus minus 0.111 into 2 power minus 1. So what is the second step? Is to add the significance. What is significant? Is a fractional part or Mantisha part, or the significant, not the whole part. That is, you should remember, add the significance. The significance is a floating point number, right. So what is a floating point number here? It's a 0.0, right. We are skipping that 1 which is a whole number, we are taking only the significant 0.0. So here that is a minus value, minus 0.111. So we are going to be add these two values, never to be add the negative value into the positive value directly. What should we do? We are taking the 2's complement of this negative value. That is a very important step we have to follow, right. What is the value? It's a negative value. So we have to convert this into the 2's complement value. This is a positive number, this is a negative number. So negative number should be added, we have only the adder in the circuit. So negative number should be taken to the 2's complement. So how to take a 2's complement? So this is a value of minus 0.111. So the 1's complement we have to taken, all the 1 should be converted into 0, all the zeros are converted to the 1. You just negligible of this whole part, we are taken only the 1. So 0.000, that is a 1's complement value. This is a 1's complement. We are only doing the significance, this is a fractional part. Now there is 1 to be added for 2's complement. So 0.001, this is a value of 2's complement. 2's complement. So now we are taken a 2's complement of 0.001. That 001 should be added here. So instead of negative 0.11, so 2's complement value we are taken, right. So what is the value of 2's complement? Yes, it's a 0.001. So now we can add the significance, both are positive number, we can add. So what is the value? Sum of the values 001, 001 of 2 power minus 1. You never to be skip of the exponent, that is a very important part, right. So 0.001 into 2 power minus 1, right. So this is a significant value, this is a significant value, right. So significant, after adding the significant, 0.001 into 2 power minus 1, right. Clear? So very clear, we have to take this negative number, that should be taken the adds complement, 2's complement, then only have to add the significance, right. So now what is the third step? It's a normalize, normalize the value, normalize the sum, either by shift left or shift right. You are doing incrementing or decrementing, based on that you have to do the normalizing of sum. So what is the value of here? 0.001 into 2 power minus 1. What is normalized? As I told, there is no leading 0 in the whole part, so we must do the one single binary bit to be on the left side, right. So now what we do, that is 1 is here, we have to doing the shift right, the precision point is here, the one shift right and another shift right and another shift right. So how many shift right we are doing? 3 point of shift right, 3 point of shift right. So when you are doing shift right, it's a decrementing the value, it's a decrementing the value. So how many points we are moving that? Yes, it's a 3 points. So minus 3, minus 3. So what is the value now? Is 1.0 into 2 power minus 4. So this is our normalization value. Clear? So here we have 0.001. The 1 is here. We are doing the precision point of shift right. This point is going to be moving 1, 2, 3. So we are decrementing the value. So the existing exponent is minus 1. We are doing the minus 3. We can get the minus 4. So 1.0 is a 2 power minus 4. 2 power minus 4. Right? Now we are checking the overflow, underflow, checking overflow, underflow. So what I told earlier, that is when the values lies between 126 to plus 127, there is no overflow and underflow. So what is the value of exponent? Is a minus 4. You never to be take the value of 2 power minus 4, only the exponent value which is 2 power n, that is the n value is minus 4. The minus 4 will be checking to this minus 126 to 127. So there is no overflow and underflow here, no overflow or underflow here, right? No overflow or underflow here, right? So now again after the steps we have to check the normalization. Still that is a normalized, that is 1.0 and 2 power minus 4. Yes, normalized, there is no leading 0 of this part, so still normalized. So still normalized, we are stopped here, we are done. So what is the value of addition of 2 floating point number, that is 0.5 is plus negative of 0.4375, that is 1.0 into 2 power minus 4. So this is a floating point addition algorithm. Now we can check this value. You can check with the decimal value. You can compare with the decimal value whether we are getting the correct binary or not. So how it should be? So this is our value. So what is our value of binary after adding this? That is 1.0 into 2 power minus 4. So this is the addition of this value. Now some of the students may can get whether this value is correct or not, the sum of the value. So very easy, you have to compare this value into the decimal. So how it should be? The 0.5, which is minus, right, normal minus of 4375. So what is the value actually when you are doing the addition is manually? So what is the value here, right? So 10, 5, right, 9, 7, 2, right, 8, 3 is correct. It's 5 is given to of 10, 10, 10. So 10, 5, 9, 2, right, 8, 3, right, which is correct after doing the subtraction. You please check whether we are subtracting the correct value. The 10, 5, it's a 9, 9 minus 7 is 2, right, it's 8, 8 minus 3 is 5, so 4 minus 4 is 0, right, 4 minus 4 is 0, right. So now checking this value, it's 1.0 into 2 power minus 4. So how to convert this as a decimal value is 2 power minus 4. So you have to take on the largest value. So what is the value? We have to do the minus 4 to be equalized to plus 4, right. When you are adding plus 4, then only it will be a 2 power 0. So if it is plus 4, what should we do? We have to shift left of 4 digits of your precision point. So 1 point, that is shift left 1, 2, 3, 4, right. So what is the value of? It's 0, 0, 0, 1, right, into 2 power 0. So into 2 power 0, right. The point is moving here, it's a 2 power 0. The whole value we are doing here. So how to take this into converted into the decimal number? This is 2 power 1, 2 power 2, 2 power 3, 2 power 4. So what is the value of 1 here? It's 1 by 2 power 4. 1 by 2 power 4. That means 1 by 16. So what is the value we can get? Either we can get of the value, right. The 9 value I think is a 625, right. Please convert. It's 1 by 16. What is the value? 1 by 16. It may be a 0.0625. So here we can get it's a 625. Right? Correct? It's a 0.0625. So this is we can get the value of, we are getting the correct value of binary number of decimal part. We can easily check with the value. You please check this value, the subtraction and 1 by 116, it should be equal of your value. So our binary addition of floating point number it's correct. So this is one of the way. That is not algorithm, but we have to check whether the answer is correct or not. We have to check. This is not in actually the algorithm. This is for your reference. You can get into the clear idea whether the value is correct or not. You may check with the value, right? So this is a floating point addition, what we do earlier. So let me recall all the steps. So before moving to the floating point addition, we must know what is floating point number, what is the number of representation of single precision or double precision. Single precision is 1, 8, 23 of the sign, exponent and fraction. 1, 11, 53 of the value, or 52 is a value of double precision. Right. So what is a floating point addition algorithm? It's a 4 steps, the mandatory steps. The first one is comparing the exponent, equalize the exponent value. Then we have to do with the second part of add the significant. Only the significant values should be added. If it is any one of the number is negative, we must take the 2's complement and do the add the significance. So once you are finishing the significance, we have to normalize the value, either shift left or shift right, incrementing or decrementing. We have to normalize. No leading 0 in floating point number. Then we have to check whether there is an overflow or underflow. If it is lies between the value minus 126 to plus 127, there is no overflow, underflow. If it is the value exceeding these two values, there must be a exception of your addition. Right. So after checking that, you have to check still normalize. If it is normalized, we are finishing the algorithm. If it is not, again you have to go to the third step of normalizing the value. Right. So that is what is a floating point addition. The floating point adder is a circuit, is in a computer architecture. We can do the floating point addition. Right. So thank you one and all for giving this session. It's very fruitful. Thank you.